Hello students, welcome to this video. In this particular video I am going to explain the horizontal axis wind turbine or HAWT in module number 4 wind energy, where we are going to discuss about how horizontal axis wind turbine is going to work and what are the types of horizontal axis wind turbine and what are the advantage or merits and demerits of these horizontal axis wind turbine. Okay. Horizontal axis wind turbine HAWT. The common wind turbine with a horizontal, which means it is a horizontal or almost horizontal in axis. The simple principle is very simple here, but the design of a complete system, especially a large one that will produce economical electrical power, is complex. Okay, so not only the individual components must be individual components such as rotor, transmission, generator and tower must be efficient as possible, but these components must function efficiently in combination. That is very important thing over here that we have to consider. So some of the main design consideration will be discussed in later in this particular video, but we should know a very important thing is in this type of turbine it is possible to catch more wind and so the power output can be higher than that of vertical axis. But in horizontal axis design, the tower is higher and more blade design parameters have to be defined. But some of the horizontal or these horizontal axis wind turbines are having a blade, one single blade or double blade or multiple blade, more than two or three. Okay, depends upon the requirement. So it requires very high altitude towers that you can able to see from the picture. Okay, so we will discuss what are the types of horizontal axis wind turbine later. Before that, we will discuss important design consideration or components of horizontal axis wind turbine. Okay, so the common wind turbine with a horizontal or almost horizontal axis wind turbine is as shown in figure. Okay, so here you can able to see the important components like is having blade, hub, then cabin or cabin, then tower. Okay, so mainly the rotor is very important design consideration. Okay, so rotor and turbine blades. A wind turbines rotor may have any number of blades which may be made from wood, metal or composites of several materials including glass, reinforced plastics, etc. Future blades may use carbon fiber which combines light weight and flexibility with immense strength. Okay,
So in the most common type of machine, the rotor is mounted on a horizontal or near horizontal shaft, and connected to either to a generator or some mechanical devices such as water pump or heat generator. Okay, the whole assembly is mounted on a tower so that it turns clear of the ground and away from surface drag and interference. Okay, so the from a performance point of view, the taller the tower, the better the taller tower better, because wind speed increases with height. Okay, mainly they have aerofoil type cross section. Okay, and the blades are slightly twisted from the outer tip to the rotor to reduce the tendency of stall. Okay, so horizontal axis rotors can be either lift or drag devices. Okay, so lift devices are generally preferred since for a given swept area, high rotational speeds and more power output can be developed by a lift than drag force. Okay, so in general, drag devices cannot move faster than the wind velocity, while a lift device can move faster than wind velocity. Okay, thus a lifting surface can obtain higher top to wind speeds, and consequently a higher power output to weight ratio, and for many applications a lower cost to power output ratio is also preferred. Okay, so lift devices use slender blades with an aerofoil section that generates aerodynamic lift. Okay, so aerodynamic lift when it is placed on the air current, or placed in an air current, and drag devices are those, or like the familiar multi-bladed farm wind pump that rely essentially on drag forces to extract energy from the wind. Okay, so rotors that rely on lift are capable of running or turning at very high speeds, as stated. Okay, so small rotors can spin at 400 to 500 revolution per minute rpm, with blade tip speeds of several hundred kilometer per hour, that is normally 8 to 10 times faster than the wind. Okay, so very large aerofoil rotors can run or can turn much more slowly, typically 20 to 40 rpm, but the blade tip speeds are comparable, 65 to 110 meter per second, or it will cover up to 250 to 400 kilometer per hour. Okay, so drag devices are less efficient wind energy converters, and always turn more slowly than the wind. They work best in less widely inland locations. Okay, less widely inland locations, but the faster they run in more, or they run the more they spill in the wind. Okay, so lift devices are, on the other hand, are able to profit from the high power densities that are available at high speed, high wind speeds. So the ratio of the power extracted by lift devices to track devices is usually greater than in the ratio of 3 to 1 for the same swept area. Okay, for this same swept area, it will be in the ratio of 3 to 1. Therefore, drag devices are often capable of generating high torques, that means twisting forces, and are ideal for some uses such as water pumping. Okay, so they are less suitable for electricity generation. It is not best suited for electric generation, which requires very high rotational speed. Okay, so in terms of several thousands rpm. These reverse is generally true for lift devices. Okay, so small rotors can often rotate such speeds, and that they can be connected directly to the generator. Okay, so larger rotors require step up gearing. That's why it requires step up gearing. Okay, so one major disadvantage with the rotors is with the slender aerofoil blades is that they will not start up without first being rotated to generate lift. Okay, so therefore it requires some external source of power. Okay, so that is about rotor or turbine blades. Then we can then second important component is hub. Okay, hub is nothing but, and here before going to explain about hub, we should know about blades. Okay, so wind turbine have been built with up to 6 propeller type blades, but 2 and 3 bladed propellers are most common. Okay, even you can able to see one bladed rotor with a balancing counterweight, and has some advantage including lower weight and cost, and simpler controls over multi-bladed type windmill. But however, starting requires high wind speeds, and vibration and other forces can be large in case of single blade. So the turbines with the 3 blades have been used in several wind energy conversion that we will see later. Why? We will see how exactly 3 blade wind mills will looks. So it will used in order to avoid the vibration experienced with the 2 bladed rotors. Okay, so these vibrations are related to the turning, that means yawing. Okay, of the rotor in order to face it into the wind. Okay, so it appears that the problem can be however, that problem can be overcome by controlling the yaw rate, whereby because they cost less to fabricate in large sizes, and are capable of operating with the high tip speed, that means tip speed ratio. So two bladed systems are receiving major attentions. Because of that, two bladed systems are receiving major attention. So you should know the blade design also. So wind turbines blade have aerofoil type cross section, as I mentioned earlier, and a available or the variable pitch. Okay, so they are slightly twisted from the outer tip to the root. That means where the blade is attached to the hub. Okay, to reduce the, why it is twisted, because to reduce the tendency of the rotor to stall. Okay, so in a few devices the blades had a constant cord length, that is constant distance from edge to the edge to the other edge. Okay, so as a general rule, however, for better performance is obtained with the blades that are very narrow at the tip than the root. Okay, so we should know how this uh, blade design is very important. Then about hub, it is a central solid portion of the rotor wheel which is known as hub. The central solid portion of the rotor is called as hub, and all the blades are attached to the hub. Okay, so it is we can say it is one type of connection to the rotor. Pitch control mechanism is provided inside the hub. Okay, one minute. And that hub is placed in knuckle or cabin. Okay, so this knuckle or cabin is the rotor is attached to knuckle mounted at the top of the tower. Okay, and it consists of rotor brakes, gearbox, generator, electrical switch gear, and control, etc. Okay. Next about control or techniques of HAWT. In that yaw control, this is very important one, yaw control. So the area of the wind streams swept by the wind turbine is maximum when the blade face into the wind. Okay, so adjusting the knuckle about vertical axis to bring the rotor facing the wind is known as yaw control. So this is achieved by controlling arrangement, uh, which is when the wind direction changes, a motor rotates the turbine slowly about the vertical axis so as to face the blade into the wind. Okay, that is actually the process called yaw control. For localities with the prevailing wind in one direction, the design of a turbine can be greatly simplified. Okay, but the rotor can be in a fixed orientation with the swept area perpendicular to the predominant wind director. Okay, or wind direction. Okay, such a machine is said to be yaw fixed, and that is, it can be rotated around a vertical axis perpendicular to the wind stream. Okay, so most wind turbines uh, are yaw active or yaw controlled. That is to say, as the wind direction changes, they will track the changing direction of the wind and they will work or they will face the wind. Okay, in this case the motor rotates the turbine slowly about the vertical axis so as to face the blades into the wind, and the area of the wind stream swept by the wind is then maximum. Okay, so in the smaller turbines, yaw control is controlled by tail vane. Okay, by tail vane, similar to that in a American pumping windmill. I hope all of all of you have seen. So in a larger machines, this servo mechanisms operated by wind direction sensor control or servo mechanism operated by a wind sensor or wind direction sensor controls the yaw motor, and that keeps the turbine properly oriented. Okay, so it is continuously orients, that means it is continuously orients the rotor in the direction of wind. Okay, the next is pitch control. So pitch of the blade is controlled by rotating it from its root where it is connected to the hub. Okay, so pitch control mechanism is provided
through the hub using hydraulic jack in the neck. Then uh, tethering control, or next control mechanism is technique is tethering control, where the wind speed rises with the height, the axial force on blade. When it attains the upper position, is significantly higher as compared to that of the lower position. Okay, so for one or two blade rotors, this causes cyclic load on a rigid hub, leading to fatigue. So this is greatly relieved by providing a tether hinge, which is pivoted within the hub, and the load is greatly relieved. Okay. Apart from this, there is one more control is there, wind stream vibration control. So wind speed variation control. So wind speed variability must be considered, especially in the design of the larger wind energy conversion mechanism. For a given turbine, there is a minimum wind speed called the cut-in speed, at which rotation is allowed to start the cut-in wind speed and the rated wind speed. Okay, so at which the generator produces its rated power, and the rotation rate is maintained constant by varying the output of the generator. Okay, so at wind speed exceeding the rated value, the rotor speed is held constant by automatic adjustment uh, of the pitch of the blades. So at very high wind speed, this blade is feathered in as in aircraft, and the rotation ceases. Okay, so the wind speed at this occurs is called as cutout speed, or it is called as furling speed. Okay, so the electric power output of the generator is essentially constant. The variation of the this generated power with the wind speed is is controlled, and this variation without any control of the rotation rate of the turbine, uh, or we can say turbine speeds. Okay, so at wind speed above the rated value, part of the available wind power is not used, okay, or spilled as a consequence of changing the pitch, or changing the pitch angle of the rotor. Okay, so these are the control techniques which has to be used in horizontal axis wind turbine. Next we will see the type of horizontal axis wind turbine. In that, as I mentioned earlier, horizontal axis with single blade windmills. Okay, so which is as shown in figure. So you can able to see there, we have only one composite blade, and there is a overweight arm that you can able to see. Then one more thing is pitch actuator is provided in order to control the pitch, and induction generator or planetary gearbox with a planetary gearbox is provided in order to control mechanical energy to electrical energy. Now, and it is mounted on a steel truss tower or shell tube tower. Okay, so in this arrangement, actually a long blade is mounted on a rigid hub that you can able to see in the sketch, and induction generator and a gearbox are also shown. If extremely long blades, to say above 60 meter, are mounted on a rigid hub, a large blade root bending moments may occur due to tower shadow, gravity, and
sudden shifts in wind direction. To reduce the rotor cost, use of low cost counterweights is recommended with to or to balance long blade
centrifugally. Okay, so rotor must move more rapidly to capture same amount of wind. So gearbox ratio is reduced. Added weight to counterbalance give some benefits of lighter design. Higher speed means more noise, visual and wildlife impacts. Blades are easier to install. Entire rotor can be assembled on ground. Okay, capture 10% less energy than two blade design, but it reduces the cost and weight of the turbine.
Adding to this, some more advantage we can able to see. Advantages like simple blade controls, because lower blade weight and cost, lower gearbox cost. So counterweight cost less than the second blade or two blades. Counterweight can be inclined to reduce the blade blade coning, and pitch bearings do not carry centrifugal force. Blade root spare can be larger diameter, okay. And we can able to see some disadvantage of this, vibration is more here. So this vibration is caused due to aerodynamic torque. So unconventional appearance, it does not look, there is no aesthetic look for this type of horizontal axis wind turbine. Large blade root bending moment can be possible. A starting torque reduced by ground boundary layer. Okay, that is one more disadvantage. One per revolution. Coils torque produced due to flapping.
Okay, so these are the disadvantages we can able to see in horizontal axis blade with a single blade windmill. Next we will see horizontal axis with the two blade windmills or two aerodynamic blades, that in the figure you can able to see here two blades.
Okay, so in this type of design, the rotor devices, or the rotor drives a generator through step-up gearbox. Okay, the blade rotor is usually designed to be oriented downwind. I hope you know that what is the downwind. We studied upwind and downwind in previous session. So oriented in downwind of the tower. Okay. So the components are mounted on a bed plate which is attached on a pintle, at the top of the tower. So the rotor blades are continuously flexed by unsteady aerodynamic, gravitational, and some inertia loads when the machine is in operation. Okay. So if the blades are made of steel, flexing reduces their fatigue life with the rotor fatigue life within the rotor. Okay, and the tower is also subjected to the load like gravitational, aerodynamic, and inertia loads. Okay, so this may cause a serious damage. Okay, so if the vibrational modes of the rotor happen to coincide with one of the natural mode of vibration, natural mode of the vibration of the tower, the system may shake, and because of this high cost of blade rotors with more than two blades are not recommended. Rotor with more than two or three or four blades would have slightly higher power coefficient
than a single blade. Okay, and uh, the overall design is complex, uh, due to or sustain the wind shock. Okay, it requires, so it is also less stable. Okay, so it saves the cost and weight of the rotor blade, but you should know tail vane is required in order to control the uh,
yaw control. Okay.
next we will see horizontal axis with the three bladed windmills or
three or multiple bladed windmills. So in this type of design, actually,
you can able to see the sketch. uh,
multi blades or three blades can be shown, which is made from metal or sheet metal or aluminum. Okay, and these rotors have high strength to weight ratio, high, and have been known to service hours of freewheeling operation in 60 km per hour winds. So they have good power question as starting torque and added advantage of simplicity and low cost. So to balance gyroscopic forces and slower rotation increases gearbox and transmission costs. So but looking more aesthetic but less noise, fewer bolt strikes. Okay, so very modern wind turbines use three blades concept. Because of this structure has a high strength to withstand heavy wind storms. Okay, and although horizontal axis types generally have better performance, they have been used for various applications, but the two major areas of interest for electric power generation and pumping water. Okay, so but they are introduced for some complexity into the design, as the mechanical energy has to be transmitted over a distance. So also in some cases the rotor motion has to be converted into
reciprocating motion. In these all aspects we can use this horizontal axis of wind turbines.